Let's now talk about the heat recovery Joule cycle, which is also sometimes called the Brayton cycle. Something we can notice in a gas turbine cycle is that the temperature at the outlet of the turbine, so in point D, is still very high. So here we can look at this isotherm, which corresponds to the temperature of point D. And one idea that can come up is that we can do something with all the heat that is still available in this hot gas going out of the turbine, instead of exchanging all this heat by giving it freely to the cold source. In particular, we can also note that in many cases for gas turbine cycle, the temperature of the outlet of the compressor, so temperature of point B, is often still quite low compared to the temperature we have in point D. So the idea of the heat recovery Joule cycle is to use this available temperature difference, so this delta T between point B and point D, in order to preheat the gas at the outlet of the compressor before exchanging heat with the hot source, because this heat that needs to be provided from the hot source is what we need to pay to run this cycle. Before going further, we can also talk about the availability of this difference of temperature, because depending on the parameters of the gas turbine cycle, there's not always positive delta T available here. For example, if we increase the pressure ratio across the compressor and the turbine, so it tends to increase the spacing between the two isobaric lines, so the high pressure will go to this direction, and it will tend to increase the temperature of point B, but also to decrease the temperature of point D, because it will be pushed down to the left. So increasing the pressure ratio will tend to decrease this difference of temperature available between point B and D, and after some pressure ratio, this temperature difference can even become negative. That's something else we can do. We can try to also increase the temperature of point C, so the maximum temperature that can be admitted to the turbine. This can be done by improving the material of the first stages of turbine, for example by cooling it actively, or by adding ceramic material onto the blades of these first stages of turbine. And if temperature of point C is increased, it will also increase the temperature of the outlet of the turbine, point D, and these things tend to increase the available temperature difference between point B and point D. So let's go back about heat recovery. What should we do now in order to use this available energy from point D in order to increase the temperature for point D? We will just add a heat recovery heat exchanger between these two flows. So here on the schematic we have the direction of the flow. So here we have the outlet of the compressor in point D, and there the outlet of the turbine in point D. And in our case we want to add one heat exchanger in the middle that will preheat the fluid after the compressor and preheat it with the flow that is coming here from point D. So that's the flow from point B, the flow from point D. that's this intermediate heat exchanger, and because the flow from point D has a higher temperature than the flow from point B, then the heat flux goes this way from this fluid to this fluid. So we now have two new points, the outlet of the heat exchanger for this flow and the outlet for the heat exchanger for this flow. We can call this B prime and this other one D prime. So this fluid has been cooled down before the exchange with the cold source, and this fluid has been heated up before the inlet of the heat exchanger with the hot source. Where do we place these two new points on the TS diagram? So one thing we can note now is that we can consider that we have equivalent heat capacity rates for both fluids. We have the same mass flow rate for both fluids because it's the same loop of fluids. And at first approximation, and it's what we have done until now, we have considered that we have a constant Cp for the fluid, so the Cp times the mass flow rate is the same for both fluids. If we have the same heat capacity rate, it means that we also have the same temperature evolution for both fluids. So the same temperature difference between B and B prime and between D and D prime. Then, if we have a perfect heat exchanger, that is infinitely big heat exchanger, then in that case it's possible to raise the temperature of point B up to the inlet temperature of the hot fluid, so up to the temperature of point D, and similarly to cool down the fluid from point D down to the temperature of the inlet of the cold fluid, so temperature of point D prime would be the same as point B, and temperature of D prime would be the same as point D. So that's what we have with the perfect heat exchanger. But we will not use a perfect heat exchanger, and this is defined with the efficiency of the heat exchanger. So the efficiency of this heat exchanger is defined by the actual heat transfer rate that is exchanged between the fluids divided by the maximum heat transfer rate that could be exchanged in a perfect heat exchanger. And this can be written only according to the temperature difference. So the actual temperature difference, if we take fluids from point B to B prime, so Tb prime minus Tb, this actual temperature difference is proportional to the actual heat transfer rate, and the maximum heat transfer rate will be the temperature difference between the inlets of both fluids, Td minus Tb. So if you have a good heat exchanger, we can reach, for example, 90% for the efficiency. So it means that point B here, its temperature can be increased up to 90% of the temperature difference with point D. So we can have point D prime, for example, somewhere there. And then similarly for the cooling down of point D, it can be cooled up to D prime, which would be somewhere there. In that case, we decrease a lot the heat that is needed from the hot source in order to bring B prime to the temperature of point C. So this strategy allows to increase quite a lot the whole cycle efficiency. Now we can also note what last thing is that having a gas-gas heat exchanger added there for the heat recovery, that's voluminous and also heavy. It means that there are some applications for which it's possible to add this kind of intermediate heat exchanger, when we have a fixed installation, for example, for electricity generation. But if the gas turbine is used, for example, for airplane engine, in that case it would be way too heavy to use this, so this kind of solution cannot be adapted for airplane propulsion.